In this video I want to talk about the Runge-Kutta method and the Runge-Kutta-Fehlberg method, which are two quite fancy methods for solving ordinary differential equations. In particular, the Runge-Kutta-Fehlberg or RKF method, that's the one that's used by SciPy's Solve IVP as their default method. So we'll start there. So it's going to be the same sort of parameters as we've seen before. We've got a function f, which is giving us the derivative as a function of t and x. We've got time limits at a and b, and then an initial value x0. And we're going to do n steps. So n is going to be 100 by default. And so h is going to be b minus a over n. So that's the length of each step. And we're going to start with x being equal to the initial value, and t's is going to be equally spaced points, equally spaced time values between a and b, n plus one of them, and then x's. So we want I would say like this, just an array of n plus 1 zeros, but I want to, if you remember the SciPy's Solve IDE thing works perfectly well with vector equations as well. So the values of x can be vectors, and your derivative function f should return vectors as well. So this line that I've written so far, that won't actually work if we try and do it with vectors. You see, if you've got vectors, if x is like a vector of length 3, then you don't want this table of x's to be just n plus 1 zeros, just number zeros. You want n plus 1 vectors of length 3, all of which are 0. So the way to achieve that, we're going to take we're going to look at we can take the shape of x, and then we put we just have the tuple n plus 1, tuple consisting of a single number n plus 1 at the beginning. So in the usual case where x is just a scalar, then this is going to produce for us just a vector of n plus 1 zeros. But if x was, for example, a vector of length 4, then this is going to give us a matrix, an n plus 1 by 4 matrix, where every row is just equal to 0. And then we're going to initialize this. This is for the value of x at time step 0. Then we're going to take n steps. So this is around time ti. And we're going to do 4 things. So firstly we're going to sort of do the Euler step. Okay, so this is going to be the slope at sort of t comma x. That's the kind of initial slope of what's going on. And then we're going to do something that's kind of similar to the midpoint method. We're going to do actually, I guess this kind of is the midpoint method. This is midpoint method sort of estimates this as a kind of this would be the derivative that we would use for the midpoint method. The value of the function f at what we think is probably going to be the midpoint of our step. But we're not going to stop there. We're going to do the same kind of thing a couple more times. So we're going to do okay, so so this m1, remember, so that's the kind of our estimate of the slope at the midpoint. So that's kind of a better thing to use as the derivative. So we're basically going to do m1 again. We're going to sort of make another attempt to find the slope at the midpoint of the interval, but we're going to find the midpoint of the interval using this m1 again. So basically we've done the midpoint step again, but with a sort of improved value of the initial derivative. Okay. And then we're going to do m3. Okay, so now we're stepping forward to t plus h. Right, so this is supposed to be an estimate of the derivative at the end of our step. So at the end of our step, t has increased to t plus h, and m2 is our kind of latest estimate of what the slope ought to be, and we're going to increase x by h times m2, and then now we're going to take the slope at this point. So now here we've got these four numbers, m0, m1, m2, m3. They're all just kind of slight variations on the same idea. They're all kind of different estimates for what the slope ought to be, at different points within this time step. And so we're going to make a kind of average of these. It turns out to be good to do it this way. Okay, we're sort of taking the average of these four values for us, four different estimates of the slope. So we've got, so that should be m1, m2, m3. We've got four different estimates of the slope, and we take the average of them, except the middle two count twice as much as the end two. And then now we're going to use this as the estimate. So we're going to our new value for x is going to be x plus this this estimate of the slope that's been attained in a rather fancy way, multiplied by the step length h. Okay, and then the end we return the t's and the x's. So of course there's a bunch of details. Why exactly are we taking precisely steps of these particular shapes, and why are we combining the different estimates of the slope in precisely this way? Well, there's actually quite a bit to be said about that, but we're not going to go into the details of that here. But there are specific mathematical reasons why this particular choice of details is particularly good, and gives particularly accurate answers in good cases. So that's our Runge-Kutta thing. So let's do an example of it. Okay, so I'm going to do so we need a function. Now I could sort of define a function separately, but let me just take this opportunity to introduce this kind of lambda notation. So here, I've got t times 1 minus x cubed, and I could introduce a new function, call it f, and define ftx to be t times 1 minus x cubed. But if I want to kind of save space and write typing, and I don't want to actually have introduce a separate name for this function, and I can just use this lambda notation. I have the keyword lambda, and a list of the variables, then a colon, and then the formula. And you can't really define complicated functions using this lambda thing, but when the return value of the function is just given by a formula, then you can do this. Okay, and then we need our other arguments. We need the time limits. We're going to do this from 0 to 4, and then the initial value. Initial value of x is going to be minus 1, and we're going to take 100 steps. So we're solving x dot is t times 1 minus x cubed from the range t is 0 to 4, starting with x is minus 1 and t is 0. And then we can let's plot it. We've got this answer here, and then we just sort of need to define t and x to be the bits of that answer. Now this actually isn't the right answer. I made a subtle mistake, which is a bit of a cautionary tale. Let's have a look back through this and see what I did wrong. Okay, the answer is that I set here, I had x is x0, and now I'm still going through all the time here, through all these formulae here with x being equal to x0, because I didn't update it. What I need to do here actually is to put in this is the previous value of x that's relevant at this stage. And I only do this just because I want to save a bit of typing. I could have just put in xi explicitly in all these parts of the formula, but I've chosen to introduce the symbol x to make it easier to read. Okay, so let's try it again. Yeah, so now this is actually the correct plot. Okay, so there's there is the Runge-Kutta method. Now we're going to go on to discuss the Runge-Kutta-Fehlberg method, which is even fancier. Okay, so what's the point about Runge-Kutta-Fehlberg method? So what's wrong with the Runge-Kutta method is that you've got a fixed step size h. But what typically happens when you solve differential equations, you find that for some time periods there's lots of stuff happening, and other time periods there's not much stuff happening. And in the time periods where everything's changing rather rapidly, you need to have a small step size to make everything accurate. But when nothing's happening very much, you can get away with a bigger step size. And so it's preferable to have a method which kind of understands what step size is needed at any given point and dynamically increases or decreases the step size as required. And that's what the Runge-Kutta-Fehlberg method does. Okay. So we'll introduce that in a minute. But the Runge-Kutta-Fehlberg, so if we go back to here, there was these various kind of coefficients that are sort of going on. There's these h/2s that are coming in here, and then there's the coefficient of 1/6 and 1/3 and 1/3 and 1/6 that are implicit here. For the RKF method, you actually need a whole bunch of coefficients. And so I'm not going to type those out. I'm going to just copy and paste from somewhere else. So here I've got these 4 matrices, which I've called RKFA, RKFB4, RKFB5, and RKFC. And so those are going to feed into the method. Now, so why these particular numbers, you might well ask? We use these particular numbers because they have a number of mathematical properties that just turn out to make the method work. And I'm not going to go through all of those, but we'll go through at least some of them are not very hard to formulate. We can if we do RKFB4, so that's this vector here. Suppose we add up all the elements in that. We find we get 1. Let's just subtract 1, so we get 0. And in fact, it works also the same for the other one, for RKFB5. And then the next claim is that suppose we take this RKFA matrix, and then I add up the entries in each row. So I add up the entries in the first row, then obviously I get 0, which is the same as the first entry in this matrix C. If I add up the entries in the second row, then I get a quarter, which is again the second entry in C. If I add up these entries here, then I'm going to get 12 over 32, which is 6 over 16, 3 over 8, and 3 over 8 is the same as the third entry there. So in fact, all the row sums for RKFA are equal to the row sums for RKFC. So let's just check that. So if I do RKFA.sum, then that just condenses everything to give me just a single number. I don't want to do that. If I did RKF.sum axis equals 0, that gives me the column sums. Sums of each column. But if I do axis equals 1, then that gives me the row sums. And if I subtract off RKFC, so then I get this. Get these entries here. They're kind of supposed to all be 0. They're not quite 0, but they'll allow 10 to the minus 16. They might as well be 0. So to avoid eyeballing all of them, let's just do maximum of the absolute values of all the entries in this thing, and we find that we get 0. So that's another key mathematical property of these matrices. Next one, a little bit more complicated. So I'm going to take RKFB4. I'm going to take the dot product of this vector with RKFC, but the jth power of RKFC, and I'm going to multiply this by j plus 1. And So what's j? Well, I'm going to take j to be 0 up to 3. Okay. So what have I done wrong here? Oh, yeah, I forgot the keyword for here. Okay. So we see that this is all giving me 1s. Okay. So just check that. Let's just subtract 1. Okay. And again, let's take the absolute values of these errors and take the maximum of them. And we see again that the error is around 10 to the minus 16. And that was for ArcFB4, and you can do it again with ArcFB5. Then in this case, it's appropriate to extend the range one further. Okay. Okay. So at the moment we're only kind of printing the last of these things. Let's print all of them. Okay, so we've got these 5 numbers. They're all more or less 0. So that's those are key mathematical properties of these matrices, and there are some further mathematical properties that are required in order for the method to work. But those ones are much more complicated to formulate, so we're not going to go into them. So I'm going to do the Runge-Kutta-Fehlberg method. Okay, so this is kind of a little bit different, and we don't initially specify how many intermediate points we want, and we do kind of potentially, at least, we specify the step h, and the way this RKF works, it might well call itself with having changed the value of h. But we might call it without an h, and if we call it without an h, then we're going to do some kind of basic thing. We'll do steps of size. Yeah, we'll do 10 steps. That's kind of reasonable default, because this is an adaptive method. So if it decides that step size is too big, then it will just decrease it. So our current value of x, we just set to be the initial value here. Now at the moment, because this is an adaptive method, we don't actually know how many steps we're going to take. And so it's not so useful to sort of try and do things with numpy matrices or numpy arrays, because they have a fixed size. I mean, there are ways we could get around that by sort of resizing arrays as required, but we won't bother dealing with that. We'll just work with lists instead, because you can just append stuff onto the end of the list as you want, and it'll grow if you need to grow. Okay. So our initial list of kind of values of x is going to go like this. And we're going to keep going. We're going to build up our list of times, and they won't be evenly spaced anymore, because we're going to be dynamically changing the step size. But we're going to carry on until we've got to the end. And how do we see whether we've got to the end? Well, we look at the last time in our list of times and see whether it's we've got to b or not. Okay, so we're going to do while t's minus 1 is less than b. And we're going to define t to be the last of these times that we've done so far. And so now we're going to need a bunch of m's, right? If you remember back to the back in the Runge-Kutta method, we had kind of m0 to m3. Now we're going to have kind of m0 to m5, and instead of just calling them M0 to M5, we're going to arrange them into a vector. And yeah, we're going to again, we're going to sort of adapt to a case where x might itself be a vector. So we want, in which case all the m's individually have to be vectors, and we want 6 of them. So we're going to put them into a matrix of kind of 6 by whatever the shape of x is. And then we're going to do kind of 6 steps, all quite similar to the steps in the original Runge-Kutta method. So we're going to define mj, that's going to be an estimate of the relevant slope, and it's going to be evaluated at a certain pair t time and an x, and the t is going to be the previous time step plus you'd sort of think, well, maybe plus h, or in the previous Runge-Kutta method, we sometimes had h's. Sometimes we just had t, sometimes had t plus h over 2, sometimes t plus h. In this case, it's going to be RKFCJ times h. Right? And if you could look back to those, these entries in RKFC, these are sort of between 0 and 1, various things, 1/4, 3/4, 12 thirteenths, 1 and then a half. Okay, so these are various points kind of in the part way through the time step. And then then basically what we want is the RKFAJ. But roughly what we want is we're going to take this matrix A and multiply this by M, and that would be good if x was just like a scalar. Then that kind of multiplication would be the appropriate thing. But x might not be a scalar; it might be a vector. So you want something that's kind of like matrix multiplication, but it's just, but it's valid in the case where the A and the M might have further indices. And the relevant thing is called tensor dot. We just need to put in the 0, 0 to tell it exactly which of the indices it's supposed to be using. Yeah, that's morally just sort of multiplying this M by the matrix RKFA. Okay, so now so here we've gone through. This is actually giving us 6 different estimates for the slope, quite like the M0 to M3 that we had previously. And then we have to sort of combine them. So actually, I guess we do np dot RKFB4 with this M, so that's kind of like an average of the various estimates of the slope, kind of similar to this thing that we did here, taking the average of different estimates to give us the overall estimate M. And then we're going to multiply this by our step length h. Okay. And now in a minute we're going to just add on this dx onto our x, or at least we might do. But firstly we need to say, the whole point about this adaptive method is that we need to estimate the error. We have to decide whether our error, whether we think we're being accurate enough. It turns out there's a way to do this, kind of using the difference between RKFB4 and RKFB5. There's a bunch of theory behind why this is a sensible thing to do, which I'm not going to explain. But so what we have to do is we do the same kind of tensor dot thing that we just did. Except that we're going to take here the different, you can take RKF B4 minus RKF B5. Okay, and we take the dot product of this with this this guy here, and we're going to multiply it by H. Okay, so now this is a kind of matrix, and we want to measure the overall size of it. We're going to use np.linal.norm. So we'll take give us like the square root of the sum of the squares. That's a measure of the overall size of this thing. And then we're going to find this number S. Yeah, so the basic question is kind of how does this epsilon is our desired desired accuracy. We wanting to make stuff smaller than epsilon, and so we compare epsilon with this error that we've just calculated, and we do something. We do different things depending on whether the error is whether epsilon is bigger than the estimated error or not. But it turns out for the precise details of what we're going to do, we don't just take this ratio on its own. We raise it to the 0.2th power and multiply by 0.9. There's some various justifications why that's a rather reasonable thing to do. Okay, so so what are we going to do? If the error is less than epsilon, then error is less than epsilon. That means that we think that the step that we've taken is reasonably accurate, and so we'll accept it. So we step the time forward to t plus h. We increase our value of x by this number dx that we came up with. And we put the new value of t on our list of times, and we put the new. Now you might say you want to say, well, we're going to put x on the end of our list of x's. It turns out that that's kind of a slightly bad idea, because x is an object, and we will. And if we just put x on the end, you can run into problems where we could accidentally, we've put that x on our list, but then accidentally we do something else that changes the x that was already on the list. So what we want to do is we want to take a copy of x, right? I mean, this is related to this kind of story about mutable and immutable objects. If we've got this x is mutable, and if we just put it by itself on the end of x, then it might get changed accidentally later. We don't want to do that. We make a fresh copy of x to put it in our list. Okay, so now so now we're going to change the step size. Okay, so what's going on here? You see, so what happens if the error is bigger than epsilon? Then what we're going to do is we're just going to run back. We're just going to ignore this step here, so we don't actually record any new values of t or any new values of x. We just run back into this loop here. But before we run back into this loop, we're going to change the step size. We're going to make a smaller step size, and then we're going to run through the loop again with a smaller step size, and then hopefully the error will be less. So how do we do that? Well, so probably we're going to sort of define the new step size to be s times the old step size. Okay, s was this number here. So if the error was rather large, then this s is going to be less than 1, and we're going to run through a smaller step size. If the error was very small, then we think, well, we could get away with a bigger step size. But in that case, s will be bigger than 1, and we'll for the next step, we'll be using a bigger step size. We do also put in this 2 times h here, because we might make the step size bigger, but it's kind of found generally a bad idea to increase the step size by too much too quickly. So we're not going to do not going to do any worse than doubling the step size. No. So that's why we put in the t plus h, 2 times h. And also we don't want to step past the end of the interval, right? So we don't want to step past t equals b. So the maximum allowable step size, we're not going to allow the step size to be bigger than b minus t. So we don't go past b as the next step. Okay, so that's basically our loop. Okay. Okay, so then we're going to, at the end, when we drop out, eventually we're going to get to the point where we've got reached time b, and then at that point, well, so at that point, t's and x's are lists. We're going to put them in to convert them into numpy arrays because it's just standard to work with numpy arrays and this kind of thing, and then we return. So that's our implementation of the Runge-Kutta-Fehlberg method. And so let's try it out. So I want to define firstly just a function of time. Okay, so here's a function. E to the minus t twice t minus 5 squared times sine 20t. Okay, so what does this look like? I mean, most of the time it's pretty small. If t minus 5 is kind of any reasonable amount, then minus 2 t minus 5 squared will be something reasonably positive or reasonably negative. So when you take the exponential, it'll be very small. So we don't really see anything happening unless you're quite close to t equals 5. But when we are close to t equals 5, what we see is this sine 20t, quite rapid oscillation. Okay, so okay, so now we're going to look at this function f of tx is minus 2x plus u of t. Okay, so what's this? This is like something that's a function that's just, if I didn't have the u of t, if I just had the minus 2x, then this is just to give you the solution would be x is e to the minus 2t. It would just be sort of dying away towards 0. But then we're kind of adding in this u of t. This is just like something that's gradually relaxing, and then around time 5 you start shaking it violently, and so it'll react to that, and then after time 5 then you stop shaking and it'll just carry on relaxing down to 0. Okay, so there's our function, and then okay, so we're going to do this arcf function. So we had f and a and b, and then actually we don't even need to supply the h. Let's leave out the h. So we're going to solve this thing from t is 0 up to t equals 10, and oh no, sorry, that 1 was the x naught, right? We did need the x initial value. Okay, so that turned out not to work because of an error that we now need to fix. Let's go back here and have a look at what's going on. So it turns out that this line here is incorrect because here we've got these RKFAJs times m. So this kind of tensor dot thing. This is going to be some estimate of the slope, and we've got x plus this slope, but that doesn't make sense. What we need to do is you have to take this slope and multiply it by the step length. That didn't make any sense to do that. Okay, so now we've modified that and gone back here. So let's go back down here again, and we'll try and solve the function, solve the problem we were looking at before. We want x dot is f of tx, solved by the RKF method. And here we go. So this is quite plausible in terms of the discussion we had before. Our function starts at 1 and it's gradually decaying, and then nothing much is happening, and then suddenly this kind of shaking comes in around time 5, and our particle gets shook up a bit, but then after time 6 or so the shaking has died away and we just continue our gradual decline down to 0. But now let's actually look at how the adaptive thing worked out. Okay, so we want to check what the time steps are. So let's we had this t's. This was the set of this is all set of all times. But what we can do is we want to get the gaps in the times. This is a fairly standard little trick for that. Okay, so one colon means we just we ignore the first time and just look at the remaining ones, and colon minus 1 means we drop off the last one. And so if you subtract those, then you'll with a thought you'll see that this is just giving you the gaps between successive times. And you can see it starts at 0.09 and then changes. Most of the time it's around 0.1, but then later on it kind of gets smaller and larger. And we can plot it. So we'll do. Actually, let's just do. So we take the shape of the t's. So that's shape t's minus 1, and then we do. We did that right. Okay, so it's just okay. So now this is showing it on the x-axis. This is just numbers, numbers 0, 1, 2, 3, up the appropriate number of numbers, and but actually there's no real. It's not really meaningful to join these things together. So let's just plot them as separate dots. Okay, so here we're seeing these are the time steps. They start at 0.1, and the solver realizes there's nothing much happening. We can get away with some somewhat larger steps, and then and actually, so it would be better. Let's go back to here. Instead, let's plot. We could try and plot. We could just try and plot the times themselves on the x-axis, but that's not going to work. The reason why that doesn't work is that we've got one more. The number of times is one more than the number of gaps. So we just have to drop off the last time. Okay. Now we can see kind of what's happening at each point. So now you can see that the time steps get bigger, get just slightly bigger until we get to this point, and now we begin to see the shaking coming in. And as the shaking comes in, the time steps get lower and lower, and they become the smallest time steps as we are around to t equals 5, and the shaking is maximized. But then after that, the solver realizes that you can get away with bigger steps, and towards the end, where it's really flattening out, you can see that there's really nothing much happening, and we can get away with a rather large step size nearly 1. And that will do for this discussion of Runge-Kutta type methods.